Okay, let's look at some important examples of resonance in organic chemistry. The most important example is probably benzene, the prototypical aromatic hydrocarbon in which, at least in one structure, you have a six-membered ring with alternating single and double bonds. Now, I could draw the benzene ring as shown with double bonds between going clockwise around the ring, C1 and C2, C3 and C4, C5 and C6. But I could draw a different resonance structure where, again, going clockwise around the ring, I could put the double bonds between C2 and C3, C4 and C5, C6 and C1. Okay, both of these are equally valid resonance structures for benzene. And in fact, when you look at the benzene molecule, it does behave as the average of these two structures. You do not actually have half of your bonds being shorter double bonds and half of them being longer single bonds. All 6 bonds are the same length, and they are all the length of 1.5 bonds. The way we indicate this notation-wise is frequently to inscribe a circle inside the hexagon to indicate the resonance hybrid for benzene, that in fact all of those bonds are the same length. And in fact, the circle is frequently easier and quicker to draw than the 3 double bonds. So you will frequently come across this notation when referring to benzene rings. All of the other examples we're going to talk about are actually ions, cations or anions. So a carbocation is a molecule in which you have a positive charge on a carbon atom. And the particular one that we want to talk about right now is called the allylic carbocation, in which you have a positive charge on the carbon next to, but not directly on, a double bond. Okay, so we have a 4-carbon chain here. We have a double bond between carbons 1 and 2 and a positive charge on carbon 3. When you get to a unit on organic reactions, you'll understand how we arrive at such a species. But for now, let's just look at it from the perspective of resonance. Can I draw another resonance structure for this ion? And in order to do that, we first want to look at the atomic connectivity. Okay, there's 4 carbons in a row, but carbon 1 has 2 hydrogens. By the connectivity, we're not including double bonds, we're not including charges, we're just looking at where the carbons are and where the hydrogens are. So carbon 1 has 2 hydrogens, carbon 2 has 1 hydrogen, carbon 3 has 1 hydrogen, and then carbon 4 is a CH3. It's actually not involved in the whole resonance proceedings. So for our initial structure, we put a double bond between carbon 1 and carbon 2 to satisfy each carbon's desire to have 4 bonds, and we left the positive charge on carbon 3. We could just as easily put the double bond between carbon 2 and carbon 3. Okay, so in this connectivity diagram, both of those carbons at present only have 3 bonds, and then that would leave a positive charge on carbon 1 and give us the second resonance structure. Okay, so this is how you get a second resonance structure when you have one of them. You simply draw the connectivity without any lone pairs, without any multiple bonds, without any charges, and look, is there any other way that I could arrange these electrons without moving the atoms? Taking this one step further brings us to the benzylic carbocation. This is where we have the positive charge on the carbon next to, but not directly on, a benzene ring. In this case, I've got the benzylic carbocation drawn in bond line drawing instead of showing all of the hydrogens. It would be instructive for you to go ahead and draw this out with all of the hydrogens. But once again, the top part of this structure looks like the allylic case, right? Double bond, and then a carbon with a positive charge, double bond, and a carbon with a positive charge. Okay, can I come up with another resonance structure of this? Well, let's do something completely analogous to what we did up here with the allylic case. We'll put the double bond outside the ring and leave a positive charge on that ring carbon. This gives us another resonance structure. But now if you look at this carefully, this cation is still allylic with respect to the left-hand double bond. So we can do the same thing again. Put the double bond between carbons 2 and 3 of the ring and leave a positive charge on carbon 4 to give us this resonance structure. And now this is also allylic with respect to the bottom double bond. So we can get yet one more resonance structure by putting the positive charge on carbon 6 and the double bond between carbon 4 and carbon 5. A final example of a carbocation that you need to be able to draw resonance structures for is what's called the oxocarbocation. And that's when you have a positive charge on a carbon that is next to an oxygen. Now, if you look at this, the carbon with the positive charge in this structure has only 6 electrons around it, but what I have done is I've put 2 lone pairs on the oxygen. Looking at how we draw Lewis structures, could I not have drawn a Lewis structure where I give the carbon 4 bonds? In other words, one that looks like this. The answer is yes, I can have 4 bonds to carbon, but for this structure now, I only have 2 electrons left to put on the oxygen, so the oxygen will only get 1 lone pair, and because it is forming 3 bonds, it needs to have a positive charge. Okay, so we have 2 resonance structures for the oxocarbocation, the left-hand one with the positive charge on carbon, and the right-hand one with the positive charge on oxygen. Finally, we have an important anion to consider that's called the enolate anion. And this is where we have a negative charge on the carbon next to a carbonyl group. Now, in order to have a negative charge on carbon, that carbon has to have a lone pair. So there are still 8 electrons around this carbon, even though the carbon is only forming 3 chemical bonds. Okay, so can we do anything to reorganize the electrons in this structure to be able to come up with a second resonance structure? And the answer is yes. Instead of having just 3 bonds to this carbon, we can once again draw a structure in which that carbon has 4 bonds by drawing a carbon-carbon double bond. Now in this case, we have to break another bond. We have to break the carbon-oxygen double bond and put 3 lone pairs onto the oxygen and put the minus charge onto the oxygen. Otherwise, if we still had a carbon-oxygen double bond, there would be 5 bonds to the carbonyl carbon, and we know that we can't have that. So looking carefully at these examples in which we have charges, all of the additional correct resonance structures have the same number of charges and the same type of charge as the original structure, whether it's a single positive charge or a single negative charge. So you're never going to change the type of charge. You cannot change the number of electrons total in the structure. That's going to have to be the same. And you can't move any of the atoms. In all of these cases, all of the atoms, even the hydrogen atoms, which may be small and are not always drawn out explicitly, but those hydrogen atoms are all there and they're all in the same place in all resonance structures. And finally, all of these correct structures, the octet rule is still obeyed. We don't have any carbon atoms with 5 bonds on it because that's something that would be strictly forbidden.